Hello, and thank you for listening to my talk, which is titled Dark Matter from Preheating, and is based on my collaboration with Matthias Pierre, currently at DESI, and Sarunas Berner, currently at the University of Minnesota and about to move to Florida. This talk is based on a paper that appeared on the archive precisely today. The focus of our work is to explore a dark matter production mechanism in which these dark particles are never in thermal equilibrium with visible matter due to a feeble coupling with them. These kind of particle production scenarios are known as Fibly interacting matter-particle (FIMP) models, and the motivation to study them is born out of the current failure to find a convincing direct detection signal for WIMP-like particles. Now, a FIMP particle is never then in thermal equilibrium, is not produced through thermal freeze-out, but via freeze-in, which is short for saying that its abundance is frozen as soon as the particle production rate is suppressed. It would trivially evade any direct detection bounds, although it could have measurable indirect signals, such as late-time decays. And its phase-space distribution would contain a snapshot of the dynamics that were shaping the universe at early times. In this talk, I will focus on one of the simplest possible FIMP scenarios, which corresponds to a scalar particle that couples only to the inflaton and which can therefore be produced only during inflation and reheating. The model setup is the following. For definiteness, we consider an inflationary sector with a T-model attractor potential compatible with CMB observations, and we note here the normalization constant lambda. The dark sector corresponds to a scalar that can couple directly to the inflaton with strength sigma via a four-leg vertex and which couples minimally to gravity. The visible sector will be modeled as a light fermion field to which the inflaton can decay perturbatively. The inflaton potential is quadratic near its minimum, and therefore the oscillation of the inflaton during reheating mimics a matter-dominated era. As I just mentioned, the dissipation of the inflaton to standard model particles will be assumed to proceed perturbatively via two-body decays with a decay rate determined by the effective Yukawa coupling Y. Then the continuity and Friedmann equations will describe the decay of the inflaton from the end of inflation to the end of reheating, which is determined by the moment at which the radiation and inflaton energy densities are equal, and defining in turn the reheating temperature. For the dark sector, the effective equation of motion, which is written here in Fourier space with P denoting the comoving momentum, contains an oscillating term proportional to phi squared. In the absence of expansion, such an equation exhibits the phenomenon of parametric resonance. Every zero crossing of the inflaton results in a non-adiabatic excitation of the field chi, which is manifested as a jump in its oscillation amplitude. Furthermore, upon quantization, the corresponding occupation number grows exponentially fast with time due to each jump. Including the effect of expansion, shown here as the decay of the amplitude of the oscillation of phi, the resonant growth can still exist, but it is disordered since the resonance is not always in phase. Now, perturbatively, the phase-space distribution of dark matter chi can be determined from the solution of the Boltzmann equation. Here the uppercase P denotes physical momentum and C is the collision term. In this picture, particle production corresponds to the dissipation of the classical inflaton condensate, whose motion can be decomposed into the product of a decaying envelope and a periodic function. For condensate, the phase-space distribution is a delta function, and the amplitude corresponds to the transition from the coherent state to the two-particle state, which must be computed mode by mode in the oscillation. The amplitude for the process can in turn be decomposed into two contributions, a gravitational one originated from the exchange of gravitons and a contact one. A careful computation reveals that both interactions have exactly the opposite phases, leading to destructive interference effects. This amplitude can be simplified to take this form in terms of the inflaton energy density and the difference between the direct coupling sigma and the CMB normalization coupling lambda. And this result can be interpreted as follows. If sigma is larger than lambda, the direct coupling controls the production of dark matter and is suppressed by graviton exchange. If the opposite is true, production is mostly gravitational, with the contact interaction suppressing the amplitude. And if both interactions have the same strength, there's a maximal interference strongly suppressing the production. Taking into account kinematic and bosonic enhancement effects, a formal exact solution to the Boltzmann equation can be found in terms of the solution to an algebraic equation that relates momenta and the scale factor. Moreover, during the early stages of reheating, in the absence of kinematic blocking, this expression can actually be evaluated analytically, resulting in a phase space distribution that decreases with the 9/2 power of momentum and with momenta which are bounded from above and below. The former corresponds to particles produced at the time t with momenta equal to the inflaton mass, while the later corresponds to particles produced at the beginning of reheating, redshifted due to the expansion of the universe. Now, to simplify the rest of the discussion, it is convenient to introduce the following notation. For any dark matter production scenario, the distribution can be rewritten in terms of a characteristic momentum B0. After dark matter decouples at the time t star, such an distribution evolves simply due to redshift. Introducing the present scale factor, the argument may be written in terms of the comoving momentum P and the rescaled characteristic energy denoted by T star. This whole argument is in turn denoted by Q. In our case, we take T star as the inflaton mass times the amount of expansion between the end of inflation and today. The comoving number density in this notation, for example, is simply given by the integral of Q squared times the distribution with an inflaton mass rescaling. And the solution to the Boltzmann equation can be written in this notation. In fact, we can extend the solution beyond the end of reheating numerically, and it turns out that a simple fitting equation shown here can be found. The perturbative result can be summarized as follows. Particles produced during reheating will have a distribution that scales like the negative 9/2 power of Q, while the exponential decay of the inflaton near and after the end of reheating leads to a Gaussian suppression in the UV. The localization of this tail depends then on the duration of reheating. This perturbative result would in principle apply to any coupling, but as we will now see, this is not the case. To get a better approximation, it is necessary to solve the equation of motion for the quantum field chi. So, introducing conformal time tau and the canonically normalized and quantized rescale field x, the equation of motion takes the form of an oscillator in Fourier space. The effective frequency is a function of time, of the bare mass of the field, of the inflaton coupling, and on the coupling to gravity via the Ricci curvature. The initial condition is of Bunch-Davies type. Now, this effective frequency contains the interference between the direct coupling and through gravity with the inflaton. The phi-dependent term oscillates during reheating, but so does R, even changing its sign. In fact, R is negative throughout inflation. Evaluating the effective frequency at the end of inflation, we find that the gravitational term is the negative of the square of the Hubble parameter. Thus, in the absence of a direct coupling, superhorizon modes will have grown during inflation due to a tachyonic instability. So, the corresponding numerically evaluated phase space distribution is shown here for different scalar masses, all smaller than the Hubble parameter at the end of inflation, in the case of pure gravitational production. What we see is that ultraviolet modes follow the perturbative Boltzmann distribution, but infrared modes dominate with a distribution that scales like the negative 3 power of Q due to this de Sitter growth. In fact, one needs to regulate infrared modes with a cutoff that corresponds to the present horizon scale. Increasing the inflaton dark matter coupling, the shape of the phase space distribution changes. For small values of the ratio sigma over lambda, the distribution is close to the pure gravitational production 1, although slightly suppressed. As this ratio approaches 1, the effective mass of the scalar chi during inflation becomes larger and larger, suppressing the de Sitter growth and finally leading to a blue tilted shape in the infrared. In all cases, the perturbative Boltzmann tail is present except for sigma equals to lambda. In this case, the interference is maximal and the distribution is strongly suppressed in the ultraviolet. Moving on to the strong coupling regime with sigma bigger than lambda, the resonant growth of fluctuations will be present, and this growth can affect the background dynamics. What we find is that spectral methods are well suited for the numerical solution of the equations of motion if sigma over lambda is smaller than about 10 to the 7 halves. Okay? In this case, the back reaction effect can be accounted as an extra term in the equation of motion for the coherent condensate phi, which is known as the Hearty approximation. And the phase space distribution in this regime look like this. As the coupling is increased, momentum modes experience stronger resonant growth, greatly enhancing the amplitude of the distribution. However, as the tail shows, the resonance is eventually shut down by expansion and subsequent particle production proceeds perturbatively. For couplings beyond 10 to the 7 halves, the resonant growth populates chi modes so efficiently that the energy density of chi becomes comparable to the energy density of the inflaton. Rescatterings transfer energy from the inflaton condensate into free chi particles and into free inflatons, resulting in a fragmentation of the condensate. These nonlinear effects require then the use of lattice methods to determine the evolution of the fields, and in this case our software of choice is Cosmology. And with it, we can determine the form of the phase space distribution beyond the back reaction regime. In this plot, one can see that during the initial stage of reheating, particle production proceeds through parametric resonance until rescattering takes over, efficiently transferring energy to ultraviolet modes and smoothing the distribution. The end result is a distribution with a quasi-thermal tail that evolves with time until back reaction is shut down by expansion and the comoving number density freezes. This tail is also a function of the coupling, with a stronger UV cascade for larger couplings. Our results for the comoving number density are summarized in this plot. At low coupling, shown here as the continuous gray and black curves, the non-perturbative computation yields the correct answer, and it depends on the mass of the dark matter field. For larger couplings, n chi is mass independent if the scalar mass is much smaller than the inflaton mass, and a minimum in the particle production is reached at sigma equals to lambda. As the coupling is increased, the production of dark matter becomes more efficient, and in this regime the effect of crossing through resonance bands can be appreciated. Finally, in the back reaction region, the comoving number density is saturated. It is worth emphasizing here that only in a very small region around sigma over lambda equals to 10 is the Boltzmann approximation accurate. With the number density at hand, one can compute and saturate the dark matter relic abundance. For weak couplings, the number density is mass dependent due to the infrared cutoff. So saturating omega then leads to a non-trivial relation between the reheating temperature and the dark matter mass. In the pure gravitational limit, omega turns out to be mass independent, and the correct relic abundance is obtained for any mass with a reheating temperature of about 34 GeV. For larger couplings, the abundance can be saturated at higher reheating temperatures up to the perturbativity bound. In the case of strong couplings, the abundance can be parameterized in terms of the mass-independent n chi, leading always to an inverse relation between the reheating temperature and the dark matter mass, which is shown here for several couplings. The clustering of curves here corresponds to the saturation of the comoving number density in the back reaction regime. To finish, I would like to briefly discuss the constraints on the parameter space coming from the determination of the matter power spectrum. As it is well known, if dark matter is not perfectly cold during structure formation, it will have a non-vanishing free streaming velocity that could interfere with the gravitational formation of structure, leading to a suppression in power, which is shown here in physical space, and here in terms of the so-called transfer function, which is essentially related to the ratio of the non-cold power spectrum to the cold matter power spectrum. Presently, the best constraints on such a suppression in the matter-power spectrum come from its non-observation in the Lyman-α forest. For the thermal relic, this imposes a lower limit of about 3 keV in the dark matter mass. In the case of a never thermalized relic, this cutoff scale is determined by its equation of state parameter, and it can be shown that this parameter depends only on the first 2 moments of the phase space distribution, and therefore one can rescale the warm dark matter bound to a bound on the mass of any other non-equilibrated dark matter candidate in terms of the phase space distribution. This bound can be calculated analytically in the Boltzmann approximation. The RMS momentum is determined by the perturbative tail, and it has the exact scale factor dependence to lead to a lower bound on the dark matter mass that is independent on the coupling to the inflaton and on the duration of reheating. This universal bound is also much smaller than the warm dark matter one, equal to about 30 electron volts. Using a second rescaling, we can actually translate this result into the non-perturbative results. In the absence of back reaction or maximal interference, the bound is independent of the reheating temperature. Our semi-analytical computation can be cross-checked with class to a high degree of accuracy. In the case of strong back reaction or maximal interference, the Lyman-α constraint is dependent on the reheating temperature. Okay? And so the allowed parameter space for dark matter production from inflation and reheating is shown in this slide. The Lyman-α constraint is shown as the dashed black line. At small coupling, the constraint is weakened by several orders of magnitude down to 10 to the minus 4 electron volts due to the dominance of non-relativistic infrared modes. At large coupling, the parameter space is constrained from below due to the efficient population of ultraviolet modes, and from above due to the overclosure constraint for reheating temperatures above the Big Bang nucleosynthesis temperature. In the middle, the Lyman-α constraint is subdominant. Masses in the gray region do not saturate the relic abundance without violating the perturbative bound on the reheating temperature. This slide here summarizes our results for weak, moderate, and strong couplings, so pause in case you want to take a closer look. Thank you.